Hello everyone, good morning to all of you. You are most welcome to the next video lecture at L&T College Multimedia Studio. Today's my topic is the chemistry of alkaline earth metals. In the previous lectures, you have already studied about the alkali metals and its chemistry. Now we shift to the other group of metals. They are kept in the periodic table. Uh, so that is group 2 elements, right? So they are called actually group second alkaline earth metals. Okay, and in the previous lectures, whatever the metals we have studied, actually they are called group first alkali metals, right? So how the chemistry of group 2 metals are different compared to the chemistry of group first alkali metals. Now in this particular lectures, we will try to elaborate the concept and understandings, the idea of the alkaline earth metals. So why, the first question is that why group 2 uh, elements are called alkaline earth metals, right? So alkaline earth metals, as its name derived, alkaline, right? So alkaline means its behavior is basic in characters, right? So because of the basic characters, okay, so it has given the name alkaline. And what about the earth metals? So all these elements such as beryllium, magnesium, calcium, strontium, barium, and radium, so they are found in the earth crusts, right? So that is why they are called alkaline earth metals. So all these elements, so they are metallic in characters and they are found in the natures as in the earth crusts. So that is why uh, they derived its name, alkaline earth metals. Now, what is the general chemistry and properties, so by which we can understand the further chemistry of these elements compared to the previous group first alkali metals? So in this particular group second, the beryllium, right? So in the previous case, actually in the alkali metals, the first metal or first element was lithium, right? So this is actually beryllium, magnesium, calcium, strontium, barium, radium. The parameters on which we will try to correlate the chemistry of these elements. So that is first one, electronic structure. Electronic structure, right? On the basis of electronic configuration, so we will justify the chemistry of these elements. So second parameter is, that is atomic and ionic radius, right? Atomic and ionic radius, okay? And the third parameter is molar mass and density, right? And the fourth parameter is, that is ionization energy. Ionization energy. Okay. And fifth parameter is lattice energy and hydration energy. Lattice energy and hydration energy. Right. And sixth parameter is reactivity. Right. So, and further we can extend the parameters depending on the time availability in the in this particular lectures. So first parameters actually is that is electronic structure. So what and in what way the electronic configuration of these metals are correlated to the previous group first alkali metals. So the atomic number of these elements are listed as 4 for beryllium, right, and 12 for magnesium, and 20 for calcium, and 38 for strontium, and 56 for barium, and 88 for radium. So these are the consecutive atomic number for these group 2 elements, right, students. And the molar mass uh, which is shown in the superscript for the beryllium, it is 9, right, and for the magnesium it has 24, and for calcium it has 40, and strontium 87, and barium 137, and radium 226, right. So this is the actually mass numbers for that particular alkaline earth metal. So what is electronic structure? So actually the electronic structure is related with electronic configuration, right. So electronic configuration electronic configuration. So when we talk about the electronic configuration for these elements, so now we have beryllium, so which has atomic number of 4, right, and this is magnesium which has 12, and this is calcium which has 20, strontium so which has 38, barium 56, and radium 87, right. So this is the actually not 87, actually this is 88. Now the electronic configuration of any particular metals look like that. That is, this is the close to the noble gas, that is helium, right? So it has electronic configuration like a helium, and the outermost configuration is 2s2, right? And for the magnesium, it is very close to neon, right? So, and this is 3s2, the outermost configuration is 3s2, okay? And for the calcium, it is very close to argon as a noble gas. Now the rest of the electrons, so occupy 4s2 configuration. Now for the strontium, so it is close to krypton, and the outermost valence electron is 5s2. And for the barium, it is very close to xenon, right? So outermost configuration is 6s2. And for the radium, so it has Rn, so that is noble gas, and the outermost configuration attains 7s2, right? So here what you are seeing, that the last electrons, so present in these elements, so they occupy s subshell, and the valence shell which contains s subshell, so all the last two electrons occupy in the s subshell, or you can say in the s orbital. So they are called s block element. S block element, right? So because of the presence of outermost valence electron in the s orbital, so they are called s block elements. Now, what is the principal quantum number for these metals? Actually, n is 2 for here, n is 3, n is 4, n is 5, n is 6, and n is 7. So what you are observing here, as the electronic configuration indicate, the principal quantum number changes when we move from top to bottom, right? So the principal quantum number is 2, and for the magnesium 3, and for calcium that is 4, and that is 5 for strontium, and similarly 6 and 7 for barium and radium, right? So what does it mean? It means in the electronic structure, at each step, additional new cell is added to the structure. Here, this is 2. So this is actually kept in period 2, and this is kept in period 3, and similarly in the 4th, 5th, and 6th and 7th periods. So this calcium, strontium, barium, and radium are kept. Okay. Now the outermost valence shell, okay, For the beryllium, so that is 2s2. And similarly for other metals, so 3s2, 4s2, 5s2, 6s2, 7s2, right? Now S subcell, so as you can see here, the S subcell, so they are completely filled, right? So S subcell, or simply you can say S orbital, or actually completely filled, and it has closed shell configuration, right? So both electron in this particular subcell or in the s orbital, they occupy the position like that. So two electrons which has up spin and down spin in that particular s orbital. So this is actually two s orbitals. So the valence subcell occupies two electrons in the s orbital. So there is no unpaired electrons in this particular configuration. There is no unpaired electrons. So for each and every metals, so there is no unpaired electrons. So they are all diamagnetic in characters, right? Diamagnetic in character, right? So as you are seeing that the valence orbital, that is s2, and 2s2, 3s2, 4s2, 5s2, 6s2, and 7s2. It means all these metals possess a valence electron equal to 2. So the valency of these metals is 2, right? So now what other factors so that can be extracted from the configuration is that, so the electronic configuration of the group first alkali metals, so that was NS1, right? And for the group 2 alkaline earth metals, so it is NS2, where N is the principal quantum number. So here s orbital is half filled. Here s orbital is completely filled. So completely filled orbital has maximum stability in the lattice structure of the metals. So these metals possess NS2 configuration. So because of the closed shell configuration, they are all stable. However, reactivity is less compared to group first alkali metals. So here NS1, the valency is 1 for the group first alkali metals. This valency electron actually tries to remove from the structure, so that it can gain noble gas configuration easily. But so in case of this NS2 configuration, because of the high stability of the S2 configuration, the electrons are not supposed to be relieved or removed from the outermost configuration. So because of the stability factors, so The first group alkali metals are very reactive because of the presence of one unpaired electron in the valence subcell configuration. So, by releasing the first valence electron, so the attains noble gas configuration, and the noble gas configuration actually they are most stable. But in case of these metals, so for the gaining noble gas configuration, these metals have to lose two valence electrons. So that is not so easy. Rather, it requires much more energy to remove the outermost valence electron. So this is the beauty of the electronic configurations of these group 2 alkaline earth metals. Now, what about the atomic size and ionic radius? So, in the previous page, as you have seen that, so for the beryllium, actually all these elements are metallic in character. So, this is actually metallic radius, which is measured in angstrom. So, it has metallic radius 1.12 angstrom for the beryllium, whereas for the barium it is highest 2.22 angstrom, and for the radium, so the data is not available in the metallic state, and it is actually because of the radioactivity for the radium. So it has short lifetime. So the major concerns or issues, so that creates the problem in the elucidation of the structure. So here we will only focus on these elements: beryllium, magnesium, calcium, strontium, and barium in this particular group. As in the previous group first alkali metals, we have also left the last elements as it was actually radioactive in characters. So we have only studies lithium to lithium, sodium, potassium, rubidium, cesium, right? So cesium was the actually bigger element in that particular group first elements. So in case of these metals, so barium is considered here is the largest metals because of the 2.2 angstrom, and beryllium appears as smallest metals in this particular group 2 elements. Here 1.12, here 2.22. So here almost 2 times size increased. It means once we move from top to bottom, what you have observed that the metallic radius increases from beryllium to barium, right? So, and the barium is the largest or biggest metal of this group, while beryllium is the smallest sized metal, and it has actually that is smaller. So now, and what will be the ionic radius, so that we will concentrate. So now each and every metals possess an S2 configuration, right? So the further stability, so that can be achieved so only by removing these two outermost valence electrons, and the resulting noble gas configurations. So, if these metals are prone to remove its valence electrons, so the next noble gas configuration which is close to that particular metals can be achieved. So, now when this suppose like that, this is your beryllium, here configuration, the full configuration in 1s2 2s2. Now if this is removing its 2 electron, now it turns into 2 plus, and now 2 electron is removed. So what is the actually configuration of beryllium 2 plus? Because of removal of these 2 electrons, now this beryllium achieves 1s2 configuration. So that is the configuration of helium, which is the closest to the beryllium. Now helium is a noble gas and which is much more stable. So these elements after the removal of 2 electrons actually attains noble gas configuration. But in case of alkali metal group first elements, the only one valence electron was removed from the outermost configuration, so that they have attained noble gas configuration. Here 2 electrons are removed from the H elements. So now it means the bivalent M2 plus type, so they form M2 plus type of the ions. Right. So it means beryllium 2 plus. So this is actually beryllium 2 plus, right? And similarly, this is for barium 2 plus, and this is for radium 2 plus. Similarly, you can write also the middle elements in the ionic form. So beryllium 2 plus, what is the ionic radius? That is 0.31 angstrom, and in the ionic state the chemistry is some sort of simple. So we have also shown the value of radium 2 plus, here 1.48 angstrom. So what this value actually indicates, the from the top to bottom, it is always the values are increasing, right, from 0.31 to 1.48 angstrom. What does it mean? The ionic radius, right, 0.31 to 1.48 always increasing. So the increase in ionic radius, and it is because of the actually extra cells or extra subcells present at each step of the last configuration. So the smallest size actually metal, so that is actually beryllium, which exists as beryllium 2 plus, and the largest size metals is radium 2 plus. Then now what is the order of ionic radius for the bivalent alkaline earth metals? So beryllium 2 plus is smallest element, and now next one magnesium 2 plus, Now calcium 2 plus, and now is strontium 2 plus, and now so that is barium 2 plus, and now radium 2 plus. So this is the order of increased ionic radius for these particular metals ions. So Be2 plus is the smallest sized cation, and radium 2 plus is the largest sized cation. Now, what is the effect of size on that particular metals is that, now suppose we have actually beryllium 2 plus, right? As these metals are bivalent, so it acquires 2 positive charge after the ionization to attain noble gas configuration. But in the previous case, group first alkali metals, what you have observed, actually they are M plus configuration, right? So because of the univalent nature, so they were all M plus configuration. So B2 plus, what does it mean? First is charge, right? So charge increased as compared to lithium. Suppose we have a lithium plus, right? Here in case of lithium, so that is plus 1 charge, but in case of beryllium, here is 2 plus charge. So the charge is increased compared to group first alkali metal cations. Now the effective nuclear charge, right? So effective nuclear charge is increased in case of bivalent cations compared to univalent cation. So if the charge or if the nuclear charge is increased, then it can impose more effective and strong force on the rest of the outermost electrons. So what is result? If the nuclear force is very, very high, so the outermost electrons in the ion, they will be strongly bound. So they will be strongly attracted towards nucleus. So the size is actually reduced. It means lithium plus is larger than the beryllium 2 plus. All the previous group first metal cations, so they are actually larger than that of the group 2 alkaline earth metal bivalent cations. So because of the increased charge. So if there is increase in charge on the nucleus, so the size is contracted, right? And rest of the outer electrons, they are strongly attracted towards the nucleus. So they are always is smaller than the group first cation. Right. So this is the actually effect of the configuration of NS2 like alkaline earth metals. Now, what is actually ionic radius? So, in this way, ionic radius increases, right? So, what about the next, that is molar mass and density? Molar mass, as you can see here, that is actually written as a mass numbers here. We have not shown in the fractional form, just for the sake of the simplicity of the chemistry, we have shown here mass numbers. So, in case of berylliums, right, so it is actually 9, and it is 24, it is 40, it is 87, and 137, and it is 226. What these data, these values indicate actually, so radium 226, right? So it has the large mass numbers. So it is the heaviest element of this particular group 2 alkaline earth metals, and this beryllium, which possesses only mass number, that is 9. So it is the lighter element in this particular group. So beryllium is the lightest element, right? While radium is the heaviest element of these particular group 2 elements. So what is the rest of things? Now mass number increases, it means molar mass increases, and the stability of this actually metals because of the metallic bondings. So the lighter element is beryllium, but in the previous case, the lightest element was lithium, so which has only mass number, that is 3Li7. So 2 unit is extra for the beryllium. So beryllium is little heavier compared to the lithium, right? So in case of previous group first alkali metals, you have observed that lithium, sodium, potassium, so these are 3 elements, actually they possess lower or lighter than the water also, because the density of these elements, lithium, sodium, potassium, they were observed as little lower than that of the water, but rest of the elements like rubidium, cesium, and francium, so they were observed as greater than the density of the waters. So because of the lighter nature of the first 3, lithium, sodium, potassium, so they were highly reactive, and they can react violently with the air or water or moisture in the environment. So in the similar fashions, what actually happens in case of beryllium? So in the beryllium, the density the density was actually extracted as 1.85 gram per centimeter cube, and in case of radium, so that is radioactive in character, it has very high density, 5.5 gram per centimeter cube. So what you are seeing here, the density of these metals increases from top to bottom. So why these densities are increasing? So for the lowest density metal is actually beryllium. It has only 1.85, and for the radium it is 5.5. Now the largest density metal is radium, and the lowest density metal is beryllium, right? So as you know that these values are actually larger than that of the density of the water, and water has the density, you know very well, that is 1 gram per centimeter cube. So it is they are heavier than water. So all these elements or metals are heavier than waters. So if these metals are added to the water, they will easily go into the water and settle down in the bottoms of the waters, right? And depending on the reactivity, they can react vigorously or violently, or it can um, catches fires. So depending on the behavior of the actually metals, so density always increases from top to bottom, and least density for beryllium and highest density for radium so were observed from these datas, right? And actually why density increases? So you can see uh, as you know that, so that is density is equal to mass upon volume, right? So this is the actually formula for the density. It means the density is directly proportional to mass, or you can simply say molar mass or mass number, right, for these groups, and it is inversely related to the volume of the so this volume. And now if all these elements or metals or since in the S block, so they are all spherical in nature. So as the atomic radius, or you can say ionic radius, both uh, are increases from top to bottom. So ultimately the volume here you can say 4 by 3 pi r cube, where r is the atomic radius or ionic radius for the group 2 alkaline earth metals. So if radius increases, then volume increases, right? So if radius increases, then volume increases, and if the volume is found to be increased, then density is lowered, right? So actually the first element, beryllium, right? So possess it is the smallest element. So smallest element, or you can simply say in case of ionic form, that is Be2 form, so the volume will be small, or simply you can say because of the lowest ionic radius, so the volume is small. For beryllium, So the density looks little larger compared to the group first alkali metals. So because of the size factors, and all these, since all these metals like beryllium, magnesium, calcium, strontium, and barium, and radium is the radioactive. So we are considering these metals. All these metals are very highly closed packed, and because of the a smaller size compared to the group first alkali metals. So uh, these metals are highly closed packed in the metallic lattice. So they are actually densers, and in the this is because of the 2 plus charge. So this 2 plus charge, the electrons are actually more strongly that is interacted towards the nucleus, and because of the high nuclear force. So these metals are actually highly closed packed structure, and mass number are always larger than that of the mass number of the all alkali metals. So it is directly proportional to mass. So density is high compared to the group first alkali metals, and the high density is actually compared to waters. So all have higher density. So that is density greater than actually group first alkali metal, right? So these elements are heavier, and it has very close packed metallic structure, um, but so the density is larger than the water, right? So which is 1 gram per centimeter cube. So but these metals have lower density than water. So this is the correlation, and because of the size effect and charge effect on the um, and these metals, so densities are larger compared to the group first alkali metals, and this is because of the actually mass numbers. Here mass numbers is dominating factor for the group 2 metals. So compared to the volume, mass numbers या molar mass increases rapidly from top to bottom, and so the uh, densities were observed to be increased from top to bottom. In case of radium 226, which is the heaviest metal, so that have actually 5.5 density, so that is very large, right? So this is the actually correlation of molar mass and density with respect to the group first elements. Now oxidation state. So what is the oxidation state? Actually oxidation state right? So oxidation state, oxidation is defined as the removal of electron from its outermost shell or from valence shell, and which acquires as a positive charge on the metals. So suppose we have a metal from the group 2. So this M, suppose this is converted into M2 plus aqueous plus 2 electron. If complete 2 electrons from the valence configuration is removed, now the resultant metal acquires as a 2 plus charge. So, and because of the noble gas configuration, so it has noble gas configuration, and the noble gas configuration actually indicates the maximum stability. So outermost 2 electrons are completely removed. Now this 2 plus charge, so all these metals exhibit plus 2 oxidation state in compounds of these metals. So group 2 alkaline earth metal possess plus 2 oxidation state, while group first alkali metals they possess plus 1 oxidation state and sometime minus 1 oxidation state in case of alkalides, right? So they possess actually plus 2 oxidation state, means whatever compounds they form possess actually plus 2 oxidation state. And plus 2 oxidation state, it means all the metals gains plus 2 charge, and which enhance the nuclear force on the rest of the electrons in noble gas configuration. So they will be strongly bound to the nucleus, and further removal of the electrons are actually will be very difficult. So what you think about ionization energy? Ionization energy. As in the previous lecture, we have defined the ionization energy. Ionization energy is the energy which is required to remove outermost valence electron from its gaseous state isolated elements. Now here the elements is M, right? M may be beryllium, magnesium, calcium, etc. If this metal in the solid state, suppose it undergoes sublimations, or you can say if it is heated, right? So it undergo in the gaseous state, so that is M in the gaseous state. Suppose M may be beryllium or magnesium, right? So under atomization, now these metals is converted into in the gaseous phase. Now this in this gaseous state, or you can say in this isolated gaseous metal, now electrons are flexible and they are more free compared to the solid state. So after the supplement of now again, if it is heated or energy is supplied, right? So the first electron is removed, and which gains as M plus gaseous, right? Now this M plus, suppose here, that is in case of magnesium, so there will be more clears. So this is in case of uh, for instance, we take uh, as example that is magnesium, and if this magnesium is uh, sublimated, then it is converted as Mg, that is Mg in the gaseous state, right? So once energy is heated, right? So now it is converted into Mg plus gaseous. Okay. So this Mg plus has configuration. So that is actually 3s1, and the 3s1 configuration actually it is the configuration of alkali metals. Alkali metals, right? So here is the outermost configuration is that is neon 3s2. Now the configuration is neon 3s1, so which appears as alkali metals, right? So as you know that alkali metals are, they are highly reactive, and so because of the reactivity they can further uh, lose their valence electron. So in this particular case, the ionization energy is IE1. So that is the first ionization energy for the beryllium, or you can simply say for the magnesium here. So this is the first ionization energy because of the conversion into Mg plus. Now this Mg plus is not stable, so they are reactive, similar to the alkali metals. So further, if heat is supplied, that is as a in form of delta, now this Mg2 plus, right? So in gaseous phase, again electron is removed. Now in this case, whatever energy is required to remove the rest of this electrons, so that will be IE2. So this is the second ionization energy for the um, um, group 2 metals. So similarly, all metals possess two type of actually ionization energy, that is first ionization energy, and this is the second ionization energy. Now this after the second ionization, so this attains complete electronic configuration like neon, which is a noble gas, and the most stable form is Mg2 plus. And for the removal of the electron requires very large energy, as because of the increased charge density on the nucleus. So increased charge density on the nucleus, they will strongly bound to the remaining electrons. So the ionization is very difficult, and it takes uh, 10 times, 20 times energy. So the lost stability of these groups metals are M2 plus in the gaseous state. So here ionization energy compared to the group first alkali metals, group first, and this is group second. So the ionization energy is greater for the group 2 uh, metals because of the uh, uh, comparatively smaller size than that of the alkali metals. So all bivalent cations, or simply you can say in the elemental state, so they are little smaller in the respective periods compared to the uh, elements which are present in the uh, group first elements. So because of the uh, size reduction, so ionization energy is very high, and this ionization energy actually actually very high, and because of the closed cell configuration here NS2, that is closed cell configuration, we have to break the symmetry, we have to break the little stability. So the energy which is required will be comparatively higher than the group first metals. So when we talk about the ionization energy, so that is beryllium, magnesium, calcium, strontium, barium, right? So barium, right, has actually highest ionization energy because of the small size. So actually it has in the previous lectures what I have shown, the metallic radius, that is 1.12, and in case of barium it is 2.22. So in case of that is so that is actually in case of so that is beryllium, magnesium, calcium, strontium, and barium. So it has size 2.22 angstrom, and while it has 1.31 angstrom. So because of the small size, and it has it actually suffers with highest ionization energy, and uh, because of the bigger size, the outermost electrons are loosely bound to the nucleus, so they actually feel lower or little a smaller nuclear force, and because of the screening effect or shielding effect of the core electrons or inner electrons. So the ionization is easy in case of barium. So this is the actually ionization energy order. So beryllium will be higher, and then the magnesium, and then the calcium, and then the strontium, now then the barium, right? So highest ionization energy for the beryllium, and lowest ionization energy for observed as a barium, as a general case. So depending on the structure and configuration. Okay. So now What about the lattice energy? And actually that is lattice energy. So, and because of the presence of +2 oxidation state, so they form compounds uh, in a ionic form. And suppose Mg react with oxygen in the presence of air, they form MgO, right? So in the gaseous state, MgO, that is solid, right? So similar to the actually suppose we have lithium solid state, so that react with oxygen in the gaseous phase to form lithium monoxide in the solid, right? So it forms uh, oxide compounds, so that is actually ionic and similar to the group first alkali metals. So the lattice energy actually from the Born-Lande equations, you know that delta U, or simply it can be U uh, L, UL, that will be equals to actually uh, uh, Z plus and Z minus. So that will be in directly proportional to and inversely proportional to R plus R minus. So the lattice energy actually we can erase and just we can put directly proportionals. So larger the product of the charges on the respective ions, so lattice energy will be large. And if interionic distance between cations and anions are large, then lattice energy will be low. So what in case of suppose we have a, so suppose we have that is beryllium, magnesium, right, and that is calcium, and that is strontium, and that is barium, right? So when it forms a suppose oxide compounds like MO, in the ionic state it is M actually 2 plus, and in case oxygen it is 2 minus. So here Z plus is 2 and Z minus is equal to minus 2. Now what is the product actually here? It is 2 multiply 2, so it is actually 4. So lattice energy is 4 times higher compared to the group first alkali metal compounds. So and because of the smaller size ions and hence total interionic distance is small, so lattice energy, or you can extensively say for the group 2 metals are very large, right? So group first metal compounds have less lattice energy compared to group second metal compounds. So because of the small sized ions and increased charge density, the lattice energy for the group second elements is very high, right? So in this way lattice energy can be correlated with the help of the charges and size of the cations and anions. Now hydration energy. So hydration energy, hydration uh, energy, right? Hydration energy means energy evolved when a particular ionic compound once dissolved in water, and if the ion persists in the water, so hydration energy is also directly proportional to Z plus and Z minus, and the size of the either cation or anion. So suppose or it may be R plus or it may be R minus depending on the ions. So in case of actually you know that for the group 2 metals, that is Mg, so in compound, so suppose MgO, so here charges again 4 times, right, compared to the group first alkali metal compounds. Now size of the cations are smaller compared to the group first metal cations. So uh, uh, directly we can correlate higher charge density means higher hydration energy, and lower size means it has higher hydration energy. So in simply you can dictate that all group second elements possess more lattice energy and hydration energy, and it is actually because of the increased nuclear charge and reduced size comparatively to the group first alkali metals or metal ions. So this is the way by which we can correlate with the configuration on various parameters actually. So that will help to understand the chemistry and its applications. So what is the actually flame test? Now suppose we actually want to investigate the flame test. So for beryllium, that is magnesium, and that is calcium, and that is actually strontium, that is barium, right? So the first two metals, that is beryllium and magnesium, actually they show no flame test, because in the when these two metals are heated, so the electronic transition does not takes place in the visible spectrum, and emission does not comes under also in the visible spectrum. So these two elements appears colorless, or you can say simply silvery white. So these two metals appears as silvery white, or you can say they are white. But rest of the these three metals like calcium, strontium and barium, it appears it is brick red, right? So it appears crimson red, and now it appears apple green, So the color is actually arises because of the electronic transition in the metallic lattice. It means the electrons from the valence shell to excited to the excited state, right? Excited state in their band structure. So in case of beryllium and magnesium, because of the closed packed structure, and actually all these metals forms close packed, that is hexagonal close packed, cubic close packed, and face centered cubic. This type of actually geometry have been observed for these metallic lattice. So for the beryllium and magnesium, actually they are highly closed packed, means the valence electrons are actually tightly bound with the nucleus. So once you supply yeah, or you can say when these two metals are heated in the flame, the excitation or transition of the valence electron does not lie in the range of actually spectrum, and the complementary colors, so they will also outweigh to the visible range. So that is why the emission does not appears as visible range. So they are silvery white or colorless. But once you move from beryllium from top to bottom, that is barium, these last three metals actually possess some colors, and because of the band structure, so and the outermost valence electrons, they are actually loosely bound to the nucleus, okay, and they will absorb visible light and undergo transition from valence shell to the excited state. And since excited states are actually short lived, right? So suppose this is your valence shell and this is your excited state, right? So this is, you can say, ground state, and this is your excited states. If the transition, suppose in case of actually calcium, so that is 4s 1, so it may transition can take place either 4p, 4d, 4f. In any of the orbitals it can be excited depending on the amount of energy that absorbs from the flame. And if the excited states are actually unstable, so ultimately these excited electrons, they will return back to the ground state and through releasing in the form of light. And if this light comes under the visible range, then they appears as colored, complementary to the absorption. So lost these three elements has less band gap between the valence band and the conduction bands. So less amount of energy is absorbed for the transition, and the excited states actually return back, so by releasing the light in the form of energy. So actually they possess colors. So calcium, that appears brick red, and strontium appears as crimson red, and barium appears as apple green. So depending on the absorption of the light and its complementary color when they show emissions. So these are the actually basic characteristics of the group 2 metals, and that will help to understand the further chemistry, so that is involved in the case of reactivity and complex chemistry. So in the next video lecture, we will focus and elaborate deeply to the applicability of the formation of the ionic compounds, covalent compounds, and complex compounds in case of the group second metals. So this is the way we can extend the more generalized form of the group second metals. So okay, so this is the from my side, and if this lectures I suppose if this lectures looks beautiful, beneficial, or comfortable to your brain and for your understanding or for your knowledge, then please don't forget to like, share, and comment on this particular video lectures. So, okay, thank you. Again, I will meet you in the next video lectures, right?